Hi, this is Professor Cummings, and I decided to do a video that might be helpful for people who are still trying to understand more about engineering drawings, as well as how they apply to other things like GD&T. But beyond just that, just the knowledge of understanding an engineering drawing is crucial, going not only into the design phase of engineering, but also into manufacturing and manufacturing engineering. And it goes beyond just being an engineer as well. This is a tool that's useful to a lot of different people through the engineering process. So, or through the manufacturing process, the whole life cycle of any product. So it touches on, the engineers, both manufacturing and production engineers. It goes into the different skilled trades. You need to understand blueprint reading. Sales are better off understanding blueprint reading, as well as any suppliers and outsourcing. Needs to understand how to read and deal with an engineering drawing. So I decided that this video could probably add some value to a lot of people. And if you are getting value out of these series, go ahead and subscribe, and you can look at some of my playlists and see some other videos that may actually be helpful. So to just start this out, what is the purpose of an engineering drawing? Now, a lot of people just see an engineering drawing and they immediately think, well, it's just there so I can, do one or two specific tasks. They usually think of it in terms of what their responsibilities are, whether it's to actually manufacture the component, whether it's to inspect the component, whether it's actually to quote on the component. But it has a whole variety of uses that makes it one of the most valuable tools in the manufacturing and design process. So it's a communication tool, throughout the in design and the manufacturing process. It's specifically and literally a method that you can communicate the life cycle of a product without two people actually interfacing. It has as much information on it as a well-written letter or as a video or as two people actually talking. And a well-done blueprint can communicate everything about a part. And it's essential to anyone in the manufacturing process. It works as a contract with your suppliers. I had several examples when I was working in industry where I had a part that came in and it wasn't done to specification. And instead of getting into an argument over why the part didn't look the way I wanted it to look, I could just call up the blueprint and point to the features that were in question, and there was no longer an issue with the supplier. It worked just as well as a contract. It said what my intentions were, it said what I expected, what the deliverables were. It actually communicated a lot of information that was indisputable because it was a well done blueprint. It establishes the acceptable part quality. Now, a blueprint obviously is going to have a lot of dimensions, a lot of different types of features in terms of the type of quality, the type of surface finish. So it gives you all the things that you would need when you consider this a good quality or a poor quality part as a customer. So the customer determines the quality, and that is how you determine what you're going to get as a good part through that blueprint. It helps determine the manufacturing process. Now you think, well, how does this dictate the manufacturing process? Well, a lot of the issues with tolerances that you see on the blueprint can only be achieved through certain processes. So if you've got a certain tolerance going out to a certain amount of precision, the number of decimal places that are on your tolerances, that dictates whether or not you can machine the part, whether or not the part has to be ground, whether or not it has to be polished, or whether or not it's going to be acceptable as a cast surface. So, based on the types of tolerances, the types of surface finishes that you call out, it really does narrow down and help you determine which manufacturing process is going to be acceptable. And last, it determines the inspection methodology. So again, it goes back to how you're going to clamp the part down using your GD&T. And if you want to see more about geometric dimension and tolerancing, I have a couple of videos that you can watch and a whole playlist of GD&T rules and fundamentals. But it also lets you know how you're going to clamp the part, and what features have to be held in relation to which, as well as the entire inspection process can be dictated through the blueprint. Now, what we have here is a very simple blueprint. It's for a product called a lock button plate. You can see it's 1/4 of an inch by 1/4 of an inch. There's some little idiosyncrasies in this drawing, but I think it serves its purpose. What I really wanted you to see is all the essential components of this blueprint and why it's actually a very good blueprint. It has 3 components that make up a good blueprint that actually gives it all the information for manufacturability, gives it all the information for inspection, as well as makes it a solid contract if you were to outsource this. Now let's look through some of what those 3 components are. First, it gives you a title block. A title block is the information that lets you know about the company as well as the drawing. When you look at a title block, you'll know not only what the part name is, you'll know any part numbers, who the engineer is, the scale that you're looking at the part at, and any crucial tolerances for that part. There's also a revision block. This is extremely important in terms of contractual disputes. What it tells you is what changes were made, when they were made, a date that they were made, as well as who approved those changes. So if you have a part that comes in that's not made to your current specification, you can cross-reference between when that part was ordered and when those changes were made in the revision block. So that way, it can protect you as well as the supplier of the component. And then any notes. Now, notes is a very generic term. What that is just any extra information that doesn't quite fit in the title block, doesn't quite fit in the revision block. Things such as removing all burrs, unless specified, all these sorts of information that you might need that you want done to your part that isn't going to readily be available in the title block or any place else on your engineering drawing. So let's look at a title block. So the title block, again, one of the more crucial parts of a drawing, has several components that I want you to become familiar with. So you got this title block, several things you can find. One is a part name. So let's see if I got my widget here. So you got a part name that is part of the title block. So this way everyone knows exactly what they're talking about. The company name is typically in the title block. It can be somewhere else in the drawing, but usually it's in the title block. A drawing number and a part number. This is very important. You'll see this particularly in large companies that have a lot of components that they're concerned with. This lets you know not only which drawing you're dealing with and which page of the drawing, but also if you've got different families, so you can say, okay, which part number am I speaking of precisely? The difference in part number can be the difference between 2 parts that look otherwise the same, but they might have 1 or 2 very crucial features of difference. You also have the material. Here we can see this was made out of 2024 T4 aluminum. You have the designer, as well as the person who checked it, and the date that they both did that. You have any kind of finishes. So here we've got a 125 surface finish. We also have whether it's going to have a protective coating or heat treating. You got the page numbers. So if this is a drawing that's going to be part of a series of pages, that'll show up in the title block. And you have what is here is general tolerances. So as you can see, in most drawings, they'll have a tolerance and specifications on the actual component, but if you have a drawing, a more universal tolerance that you want just carried on throughout, you can cover that in your title block. So here you've got the tolerances with the precisions, which helps you dictate what kind of manufacturing process and any type of angles, and other types of tolerances that might be universal to the part. So this is a very crucial portion of a drawing. Now, one of the more important parts of drawing is the isometric view versus an orthogonal view. And it's also one of the simplest to understand. So an isometric view, it just gives you the ability to see a part from 3 sides. It's that ability to look at a drawing and say, okay, I can look at this particular drawing here and know whether or not what features apply to the top, front, and side. So you got a top, front, and side. You also have some dimensions on it. You don't necessarily have to have dimensions on any of these views on the isometric view in particular, but this helps give you a good visual for how the component is made and how the sides all relate to one another. Now you've got an orthogonal view, and it shows the drawing, as a function from different angles. So different types of projection. So here you have this big three-dimensional letter E, and in an orthogonal view, you would have a very specific front that you're looking at, just looking at the front of the E. You have a top that you're looking at the top of the E, and then you got this side view, which gives you some ideas the side of the E. And I think I got these back. So this would be, excuse me, the front, side, and top. Okay, so that is, you could picture this as being part inside of a glass box, and as you look at one side of the glass box to the other, that gives you, whether or not you got what portion of the orthogonal view you're looking at, what you're actually concerned with. So that is the isometric view and the orthogonal view, and this will show up in all the other drawings. So these are like two general categories of drawings, and you'll see this throughout most engineering drawings. You'll have them based on an isometric or an orthogonal point of view. Now, one important thing that can be very confusing, and it's mostly, I think, confusing depending on where you learned your engineering drawing from and where you first started seeing engineering drawings, where you've actually worked, is first and third projection. Now, the first and third angle projection is just a different type of notation, how drawings are set up, particularly for orthogonal drawings. What you have here is a first angle projection, third angle projection. One is more common in the US, and third angle view is more common in Europe. In different parts of Asia. So US, and I believe just all of North America, and the third angle view, I believe, is a European and parts of Asia. Now, the way you can think of these two projections, if you consider, break the universe up with a left plane profile plane, a right profile plane, a horizontal and a vertical plane, and you think everything has to be positioned in a different quadrant of these different planes, you could start to understand your first and third angle projection. So first angle projection takes place in this first quadrant. So right here in the first quadrant. Third angle projection, you picture your object in the third quadrant. And you as the observer are always in the second quadrant. So here you are standing in the second quadrant, viewing both first and third angle projection. And your object, whatever it is you're looking at, is still in the same orientation. It's just either going to be portrayed in the first quadrant or the second quadrant. So you don't shift it, you don't twist it, you don't reorient it, you leave it in that same orientation, whether it's in the first or the third quadrant. So the difference between the first and the third quadrant from your observational point of view determines how you actually see this when you portray it in an orthogonal point of view. So let's give this a little more clarity by looking at this drawing here. So what you have here is a house, and this house is pictured within a cube, an imaginary cube. And you can think of this cube as, with orthogonal drawing, being projected onto each screen of the cube, on each face of the cube. So when you're in a first angle projection, in other words, it's sitting here in the first quadrant, you're in the second quadrant looking at this house. So that will put you over here, and you're viewing it this direction. This is why in first angle projection, you look at the front of the house, and the side, right side would fold out. If we took this panel and folded it out, that would be part of your right angle, or your first angle projection. Your top would fold up above it, your bottom would fold down below it, and your left side would fold out to the left. Now, if you're looking at a third angle projection, you would have to picture yourself as sitting in the second quadrant, or you're still in the second quadrant, but the house is in the third quadrant, and you're standing on top of the house, and you're looking down. Okay, so now the center of your drawing is going to be the top of the house. Sorry about that. Your center drawing is going to be the top of the house, and below it is the front view as it folds out. The right side view folds out to your right. The back of the house folds above, and the left side view goes out to your left. And that is the difference between a first and third angle projection. Now, another important view, particularly when you have a lot of internal dimensions on or internal features that you're really concerned with, is the section view. Now, section view, you can think of that as a glass plane or a ability to cut the part along a certain line. In this particular case, you've got a straight line going across a cylindrical part. So we identify this as plane AA. What that shows us is if we were to slice the part along plane AA, like this glass plane is showing, we're able to see the internal workings of that component. So it's no longer this simple cylinder, it's a cylinder with several passages. And what we end up with is a section view that looks like this. So it gives us the ability to see all the passages that might be going on or any type of internal workings in our component. We can actually dimension around some of these and actually understand what's going on inside of that part. And that's the importance of a section view. So it allows you to see what's going on inside of the part, while still maintaining some of your external sections. And a section view doesn't have to be a straight line. It can actually be a line that cuts across. They could have just easily, shown the section going along this in that particular path and have a 90-degree section cut out of the component. So it shows normally hidden sections of a drawing. Now the detailed view, it helps. It's a detailed view are used to gain a better view of tight features. So if you have a portion of a component that is just too tight to actually see what it is, you can actually use this detailed view, and it gets depicted in a balloon with a detailed number. So if you have this component here, whatever this particular is, looks like some sort of a welder, and you want to know what's going on in this section A. So you have a detailed view, you open it up as detailed A inside of a balloon or some sort of depiction, blows it up to a scale of 1 to 2, and now you can start to portray on exactly what is required in this component. You often see this detailed view when looking at threading, when looking at certain types of internal holes, or any type of detail that might be too small and too below scale for the rest of your drawing. So you just use a detailed view, blow it up, put it in another section of your drawing or on your blueprint. Identify it, let it know that this section A is section A or detail A, and you're able to actually depict this part of your component on the same page. Now, you also got assembly drawings. They provide instructions for how you would put that component together. Along with your title block, which is always a part of the engineering drawing, you have what is known as a bill of materials. And all a bill of material is like a grocery list of all the components of all the different details inside of your component. So let's look at this particular drawing. Now what we have here is some sort of roller assembly. You can see you've got your isometric view here, so you can see what this looks like in all three dimensions, top, front, bottom, side. But on the left and right, you have your drawing, which is no longer a single component. It's actually a full assembly of all those components. So you can see that you've got bolts, you've got a roller, and you've got a base, and you've got several things that are internal to the component that you can't directly see, but they're all depicted with these little balloons and numbered out. So you can say what part is what. Now this bill of materials is important because it lets you know not only what the component is as they correlate to these balloons, but the quantity that you're going to require and what information you're going to need if you actually order the portion. So if right here we've got detail 6 are hex bolts. They're made out of mild steel. You've got 4 of them, and this gives you your detailed information. So they're metric 10mm threads, and you have enough information that if you need to order some more of these bolts, you could very easily. Now you also have component 5, which is the roller itself. And you see this depicted here, pointing directly to the roller. It's made out of cast steel. You only have one, a quantity of 1, and it is seen in part number RA01-3. So that lets you know there's the details of this with all the dimensions, all of the tolerances, all the surface finishes is going to end up in this drawing. So this is the drawing you're going to need. And you can see that all of these components have their own drawing with all of their separate dimensions and features. But just from this one drawing, you're able to see exactly how this component is assembled and what all the parts are together and what they're made from. So this is a really important drawing because you could actually use this to actually order and buy more or get more manufactured and still know how to assemble it together. So again, this communicates all the way from the design, in this case all the way to the assembly process. Now another good drawing is the exploded drawing. Now this is a different type of assembly drawing, but it shows the components all in relation to each other and how they're going to be assembled. So it shows them kind of blown apart, hence the name exploded view. This is the kind of drawing you see if you have a component or something you bought from, say, IKEA, and you need to know how you're going to put it together. It actually shows all the components laid out and oriented so their functional relationship is played out together. So you can look at this drawing and tell, that this turbo, how everything is going to assemble. So what part goes in first, second, third, and where the bolts are going to go in, and then finally how the housing is going to be clipped on. On this portion, you've got the outer shell, depicted, blown apart, from each other. You got your outer shell, and then you got all the internal components, the exhaust housing. You got this turbine, number 5. And you got the inner housing, the nose cone, and the propeller, and how they all come together inside of that shell. So if you look at this particular drawing, I know it's a very busy drawing. We can see that pretty much everything we spoke about is here. So we've got the title block down here at the bottom. We know the company name is Engineering Graphics and Design. We got part numbers. We got the tolerances, universal tolerances and surface finishes depicted here. We got an isometric view, so we know exactly what it is we're looking at. And it's a flange housing. We know it's made of 316 stainless steel. We know it's a first order or first angle projection. We have a section view, section AA, that slices it right down the middle, and we can see the internal workings of this component. We see all the dimensions that we have here that we're going to be concerned with, the different types of threads, the different types of bolt holes, or screws. We also can see different types of detailed drawings. So we've got detail D, which depicts this portion here. We got detail C, which depicts this portion here. So now, because these are such small portions, we can see now what these snap rings look like. We can see much smaller and tighter tolerances. We can get more information on the different types of what might be an O-ring or a chamfer area inside of here that we couldn't have seen inside of this drawing. So what you can see is that this sort of a drawing, and this is a full functioning drawing of all the things that we spoke of, or most of the things we spoke of, that shows how this works in the real world now. And you can see that, knowing all of these, you can reference back and start figuring out how to make this component, how to communicate it, and if you have a part that isn't made properly, you can actually go back to your supplier and address any issues. You can also see, just based off of the tolerances, exactly what you're going to have to do to manufacture this component, and well as how you're going to have to clamp it or restrain it when you do any type of inspection. So that's some of the basics of engineering drawing and understanding an engineering drawing. If this was helpful, go ahead and subscribe to the channel, share it with anybody who might be struggling with engineering or any types of reading a blueprint. If you have any comments, please let me know if there's any type of details that you would like to know more about in terms of drawing. And any type of feedback that I could use to improve this sort of a drawing. So again, this is Professor Cummings. Go ahead and subscribe if this was helpful, and thanks for watching.